Okay, so in earlier we had discussed this particular problem, question number D1, where we had an N-type semiconductor and carrier generation in the middle, and we had asked that electron density, hole density, drift current, diffusion currents of due to electrons and holes was to be determined. Well, related to that particular problem, we have problem number D1B, where what we have is instead of the ohmic contacts, what we have is an ideal, we have an ideal insulator. We have an ideal insulator here. So we have a semiconductor and an insulator interface at this particular point here. And of course, there are contacts at this particular end and at both ends, and both of them are grounded, so that is there. But the interface of the semiconductor is not with the ideal metal contact, but with the insulator. And what we mean by an ideal insulator is that the recombination velocity S is equal to 0 here. Now, when we talk about recombination in the bulk, we usually describe it in terms of recombination lifetime tau p. Recombination lifetime tau p. But when we want to discuss recombination at the interface like this, semiconductor insulator interface like this here, then that's characterized by a recombination velocity. We describe the current at that recombination current at that particular interface. Let's say hole current will be equal to Q times excess carrier density times S here, recombination velocity. We call it velocity because it has units of centimeter by second here. You can verify that J has units of ampere per centimeter square and coulombs and per centimeter cube. And so what we have here is what I'm saying is that at the interface of the semiconductor and insulator, we have an ideal interface with recombination velocity, which is 0, which would effectively mean that if you calculate Jp at the interface, hole current density at the interface, that is equal to 0. Right? So what we would want you to do is calculate all the things that you did in problem number D1, electron and hole density and drift and diffusion current components, but with the difference that we have an insulator, an ideal semiconductor insulator interface. And what we can also have is variations on this particular problem. For example, we could have where we have on one side we have an ideal insulator and on the other side we have an ohmic contact. So that could be another interesting problem to try out. The other things that we could do is right now we have symmetry. We have symmetry here. I mean, in this case, we don't have symmetry because we have insulator and ohmic contact on the other ends. But in the previous problem D1B and problem D1, we had symmetry. The other thing we could do is that instead of generation taking place right in the middle, we could shift the generation to the right or to the left and then recalculate all of the parameters that are there here. All right, so let's stop here and enjoy solving the problem.